as a child, I worked at my father's electrical contracting or an appliance store, and so I just liked to work on whatever there. I mean, he had a lathe and a machine shop, and so I could build stuff, and so it was that background of just being around things and being around physical things. You know, whether it was running a welder or making an electric welder, that sort of got me interested in building stuff. I decided that I think probably at 12, 10 or 12, that I wanted to be an engineer. I had no idea what an engineer was. I just knew there were a bunch of people, you build all this stuff, and somebody had to do it. At NSF, we basically put the network there, but as we did it, we had no idea what it was going to be. We didn't sponsor any research about how to make it happen. All we did was, look, we're going to put this network there, and after the fact, why it's obvious what happened. But at the time, I was responsible for writing the proposal cross-government agency of having a single network that would go across the agencies, and nowhere did we get the idea of that this is going to enable this massive amount, what amounts to having all these facilities, and that these are going to be accessed by a bunch of clients. If we thought about it, was what happened is having bandwidth there reduced response time, and it enabled time sharing. So, I worked on time sharing in 1965, the first time sharing computers, and this basically said, okay, I can have a computer, I can have all this array of computers, and basically they're all shared, and so anybody can access any computer, and that's basically what the internet is. A whole set of servers out there responding to people. I was with Alan Kay a couple of days ago, and he said, I remember you giving this first lecture to this group on called SNAPS, which actually Jim Gray and I invented, which was scalable networks and processing nodes. And we envisioned basically an infinite computer that was made possible by connecting all other computers together. Computing is now composed of thousands of computers operating together, as opposed to trying to make a single computer with lots of processors operate together. I personally gave up on multiprocessors in 1994. Jim and when I met Jim Gray, I had given up on them, and Jim had the same religion about multiprocessors, that you simply can't build a single processor with a single shared memory in a timely fashion. But the challenge, I think, is going to be as we ask more complex kinds of questions, is can somebody put together a kind of a world scale model that pulls everything together, that in fact runs scenarios in the same way that the financial community runs scenarios on risk? In the cloud environment, it's really the computers are very loosely connected, but the parallelism is kind of implicit by being able to ask a lot of questions, or ask a question to on a lot of data simultaneously. So it's totally different than the traditional high performance computing. So in a way, these two are remain quite separate in terms of how they're used and what happens. The big difference in the cloud then is one that it's a supported data computer, so that it's really the value in it ultimately will be what data is in there and what kinds of questions could you ask for as a service. Science is incredibly, from a tool standpoint, is incredibly slow and conservative. And it just takes forever to get going on some of these things. But the cloud the distributed nature of the cloud, the centrality of the cloud, the fact that it's really a database, the fact that you can then ask a lot of questions on that database, and that as you have a lot of databases in the cloud, then you can start to work those things together. That's when you get some real power. And that's when you could do these massive kind of simulation I'm describing that have to do with the nature of food and CO2 and whatever. The thing about the cloud is that there's really, I think people miss a lot in the cloud about the cloud, is that in addition to having a kind of centrality to the data, there's this massive distribution of being able to acquire data from all over the world, and to have those things come in through a common networking structure, and that's already maintained and into a common data set. So the network the cloud network is probably as important as having it come in centrally. I think the machines that we're constructing today, it's hard to think of these centers that we're building as a machine. Although I claim they are a kind of a single computer because they can be used in that way. I think those kinds of machines can be employed to do simulation of scales that we've never even thought of. In the case of sort of society and the world, thinking of the world as something that we need to simulate more, that has everything in it, whether it's models, ocean models, climate models, what's going to happen to food, what's going to happen to population, all of these things. I think we need to, I think the computers we're building now should allow that kind of modeling to take place.